All right, thank you very much for the intro, Ricardo, and hello, everyone. My name is Jason Kim, and I will talk about our paper, Spook.js attacking Chrome's strict site isolation via speculative execution. So first, let's look at how people used browsers 20 years ago when I was a toddler. And by the way, that's me. According to my parents, we had separate applications for email, word processing, MSN Messenger. To be honest, I have no idea what that is, et cetera, et cetera. I've also heard that browsers were strictly for searching things on Google or shopping for books and only books on Amazon. Nowadays, we check our email in the browser. We also make documents there, send bank transfers, and look at social media. To sum this up, browsers have taken over every aspect of our lives. And because these tasks often deal with credit cards and passwords, the consequence is that browsers simply have many secrets within. Unfortunately, because browsers are important, people try to extract secrets from them. And with Spectre, disaster followed because Chrome had had a uniprocess design where several tabs were rendered in one process and therefore sharing an address space. While this design was resource efficient, an adversary could read all the information in the other tabs. In response to this, Chrome's developers introduced site isolation, which renders different websites in different processes. In this scenario, even if the attacker mounts a Spectre attack in one tab, there's nothing from the other tabs in the attacker's address space, and therefore they can no longer read secrets. And so we come to the research question that motivates our work. Have we mitigated Spectre in the browser? And I guess the fact that I'm standing here means not quite. And indeed, in this paper, we present Spook.js, a speculative execution attack to leak secrets from Chrome despite the presence of site isolation. While there are countermeasures that we must first break, we show that practical Spectre attacks in Chrome are still possible, such as the antelope we leaked below. We also show leakage on Chrome-based browsers like Brave and Edge. Spook.js works on both Intel CPUs and the Apple M1, and leaks fast at up to 500 bytes per second. So in the next streak of slides, I'll first introduce what each problem to us was, and then cover how we solved it. The first problem for us as an attacker, as you can see by this sad cat, is site isolation, as I just discussed before. In an ideal world for us, if we have an attacker tab and a tab with secrets, such as make.com, we would like to have the attacker's web page and the secret in the same Chrome process. Unfortunately, under the principle of site isolation, that different sites belong in different processes, what we actually get is to our right, where the attacker and the secret are isolated at the process level. However, we identify an edge case where site isolation no longer holds. We introduced Tumblr, a popular microblogging service, as one of our real examples. So Tumblr hosts both the accounts page and any arbitrary blog as subdomains of tumblr.com. And here we find that Chrome does not always apply site isolation to subdomains of the same page. And we call this behavior consolidation. I should clarify, consolidation is not a bug, but rather is there by design. Strictly having one process per tab can become expensive on resources quickly, so Chrome will isolate subdomains under memory pressure, since by intuition it's unlikely that two subdomains belonging to the same site will be hostile toward each other. A slightly more technical description is that Chrome will consolidate pages with the same effective top-level domain, or ETLD, which is .com in this example, plus the prefix immediately before that. And we call this grouping scheme ETLD plus 1. In general, if we have two subdomains of example.com, which are foo and bar, because they share a common ETLD plus 1 of example.com, foo and bar can be consolidated. Well, why is consolidation a problem? In addition to any arbitrary blog on Tumblr and its accounts page being eligible for consolidation, Tumblr blogs host user-supplied JavaScript. Tumblr does this so that each blog owner can customize the theme of their page. However, this also lets us create a malicious blog, package our Spook.js code as JavaScript, and make the browser run it all in the same address space as Tumblr's accounts page. In fact, it's not only Tumblr, but also Bitbucket, our university website, and Google's G Suite, just to name a few. What they have in common is that they host user-supplied code and secrets in subdomains, and these subdomains can get consolidated by Chrome. So now we've identified some practical corner cases where site isolation doesn't take place, and this makes our sad cat happy now. In an ideal situation, we should be able to leak secrets right away since they're in the same address space. But what prevents us from doing that? Next, I'll cover 32-bit addressing in Chrome. On this slide, I'll show why a Spectre v1 attack is insufficient. So to our left, we have a Spectre v1 gadget and a secret that is normally inaccessible. Well, if we mistrain the branch predictor, the CPU will speculate past the if condition and add the out-of-bounds index to the array's base pointer. This will make the result point to our secret, which then will get dereferenced. Finally, we encode the secret by accessing it as an index inside a probe array, which will bring the element at that index into the cache. We can construct a covert channel under speculation this way, because if we load each element of the probe array, only the element that was cached before will have a fast access time, and all the other elements will be slow. In summary, the Spectre v1 gadget itself looks fine until we look at the data types in Chrome's JavaScript engine. The base pointer to read from is 64 bits wide, but we cannot control its value. On the other hand, we have control over the index variable, but it is only 32 bits wide. This limits our out-of-bounds reach to 4 gigabytes, but in practice, we found the secrets we want to leak are not in this region, but unfortunately, much further away. So to sum this slide up, while Spectre v1 will work per se in Chrome, we won't be able to read anything meaningful. So in an effort to find a way out, we looked deeper into how Chrome performs array accesses, more specifically typed arrays, which we use for our exploit. JavaScript is dynamically typed, so a function that takes 2 arguments and returns their sum should be able to take in 2 integers, 2 strings, etc., etc. But this flexibility is bad for performance. So if Chrome sees a piece of code being called with one type of argument repeatedly, it will compile the code while inserting a type check under the hood. So first, let's see what happens when we give this code a typed array as it expects. The if statement, which checks the type, evaluates to true, so the pointer dereference happens without any quirks. But why is this still insufficient? Recall from the previous slide that while the base pointer is 64 bits, we can't control its value. And while we can control the index, it's a 32-bit value, so our 4 gigabyte addressing problem is still there. Therefore, the takeaway so far is that we cannot stick with Spectre v1, but instead need an entirely new gadget. Well, the 64-bit base pointer in our typed array is not accessible, which means we'll need a way around. Let's construct an object that is not a typed array, but one where we can control the value at the same memory offset that would correspond to that 64-bit pointer. So here we're effectively trying to fake a pointer. Well, what happens when we try to index into our malicious attacker class object instead of a typed array which the compiled code expects? Unfortunately, because the type is an implementation detail internal to Chrome, we cannot access it from JavaScript. So the type is first compared, and since object is not a typed array, the if evaluates to false, and execution flows to the else clause where an exception gets thrown. And that's no good because the line of code where the pointer gets dereferenced did not execute at all. So if we can't change the type to what we need, although we would have loved to do that, what can we do? The answer we devise is to delay the type resolution and make the CPU speculate past it. First, we need to flush just the type variable of our malicious attacker class object to induce speculation. And here we'll symbolize flush with a toilet. Then we can mistrain the branch predictors, just like Spectre v1, for the CPU to predict taken on that if. And this will make the body of the if statement run under speculation. But because our fake pointer is at the exact memory offset where the compiled code expects a 64-bit pointer, the CPU dereferences our fake pointer transiently, resulting in speculative type confusion. And the rest is identical to Spectre v1, where after speculation ends, we can retrieve the value which we dereferenced transiently through a cache covert channel. But wait, we want an L3 miss to happen when loading the type so that the CPU speculates, while we want an L1 hit on the fake pointer such that speculation doesn't terminate. How do we achieve this? We trick Chrome's memory allocator into placing an instance of our malicious attacker class object across cache line boundaries, and then we evict just the cache line which contains the type. So now we've overcome the 4 GB addressing problem with a usual Spectre v1 gadget by putting forth an entirely new Spectre gadget which makes the CPU transiently run code on an argument of the wrong type. What's left? And you can see our dog is now happy. But for a practical Spectre attack, the last requirement is that our gadget can be used reliably for many iterations so that we can leak large amounts of data. And for that, we need to understand the behavior of our gadget from end to end. Let's take another look at our gadget from before, where by evicting the type of our malicious object, we could make the body of the if statement run under speculation. But what happens when speculation ends? The type is brought back in, the CPU realizes it's the wrong type, and execution flows to the else clause where the code throws an exception. This is still not good because the exception means our gadget will work at most once. So how do we make a reliable gadget? We wrap the entire gadget from before into another if statement with a condition that we control such that we can mistrain its branch predictor just like Spectre v1. When speculation happens this time, the entire gadget runs under speculation not once, but twice in a nested manner. The CPU is speculating on both the outer if, colored in pink, and the inner if that checks for the argument type. Hence, even if this gadget throws an exception, the exception gets rolled back at the end of speculation and never commits architecturally. And so this way we can keep Chrome oblivious from what's happening and keep on leaking. So now I'd like to clarify at a glance what we can do with Spook.js. Our attack runs on Chrome 89 and furthermore the same version of 2 other browsers that are based on Chrome, Brave Browser and Chromium Edge. All 3 browsers are unmodified and run in their default configurations. All Spectre mitigations are enabled, and version 89 was the latest for all 3 browsers at the time of writing. Spook.js runs not only on a wide range of Intel CPUs ranging from 6th to 9th generation, but also the Apple M1. On either platform, our leakage rate ranges from 450 to 500 bytes per second, and our reads are 96 to 99% accurate. So now, what can we do with this? For our first attack, recall that any arbitrary blog on Tumblr and Tumblr's accounts page can be consolidated into one process. So here we host Spook.js on a Tumblr blog, attempting to attack the accounts page and recover a user's credentials. In addition, we assume the target uses a password manager with autofill, which is LastPass in this case. When the credentials are copied into the DOM and therefore sharing an address space with Spook.js, they became fair game for Spook.js to read. And speaking of LastPass, when we did this work, Chrome did not isolate extension processes. So this let us package Spook.js into a Chrome extension where its process became consolidated with LastPass's. In the second scenario, we were able to dump the master password, effectively compromising the entire vault. Next, we show that this happens not only with LastPass, but also with Chrome's built-in password manager, because the root cause was that when any secrets get copied into the same address space, they become within reach of Spook.js. So going away from just passwords, if you happen to have credit card autofill set, then Spook.js will happily recover that for you, too. Last but not least, we exploit that two subdomains of the same site don't necessarily trust each other. Here we set up a personal Google site and package the Spook.js code within. However, Google uploads and hosts user-supplied JavaScript to a subdomain of googleusercontent.com, let's say foo. On the other hand, if our target uploads an image to their personal Google workspace, Google will also upload and host user-supplied media to a different subdomain of Google user content, let's say bar. Because the Spook.js code and the image are hosted on subdomains of googleusercontent.com, they share an ETLD+1 and are eligible to be consolidated. This lets Spook.js read the image data and reproduce our leaked antelope to the right. And that brings my talk to an end. Thank you for listening, and I'd be happy to answer any questions.
Thanks, Jason. Are there any questions? We have time for a couple of questions. Okay.
Hi, very interesting work. I'm Kyle Zhang from ASU. So we've been talking about Speculative can be exploited from JavaScript for years. Finally, it is here. But I have a question about your work. So in your previous slides, you showed that your target is basically Chromium-based browsers. And then, but last year, Chromium introduced a protection called virtual memory cage. Does your work still work against virtual memory cage with the protections on? Have you tried it?
I believe we have not tried our exploit on newer versions of Chrome past 89.
OK, thanks.
OK, I'll ask a question. So I'm curious, how did you figure out the typed array code of Chrome? Did you have to do reverse engineering, or did you have access to the source code?
I would say it was, partially due to Chromium and more specifically V8, its JavaScript engine being open sourced. So there were a couple clues that we could take from there, but in the case of our compiled code, when we index into a typed array, I guess this was something we had to do mostly by reverse engineering, by looking at like the assembly that was dumped and figuring out what was going on.
Hey, that was a really clever attack. I was wondering, did you happen to know if any other Spectre variants are exploitable, or like what kinds of gadgets you'd be able to find when they're compiled from JavaScript?
Aside from Spectre v1, which I noted where we wouldn't be able to read anything meaningful, and type confusion, I'm not sure. That is something we would leave to future work.
All right, awesome, thank you.
OK, let's thank Jason once again.